module and wireline logging. Today we shall learn about wireline logging and its classifications as below. 1. Lithology logs. 2. Porosity logs. 3. Saturation or resistivity logs. Downhole logs represent continuous measurements of the drilled formations as a function of depth. The advantage of downhole logging is the ability to record, concurrently, petrophysical as well as structural information and several properties. Operating on an intermediate scale between core measurements and borehole geophysics, downhole logs are characterized by fast data acquisition over large depth ranges under in situ conditions. The main target of downhole measurements is the reconstruction of the drilled lithologic units. This includes a reorientation of core data based on high-resolution images. Measurements of porosity, P-wave velocity, and density allow the depiction of zones of weakness, which may subsequently influence borehole stability. A quick view estimation of logging data provides depth ranges, and, to a certain extent, lateral extension of these zones. Classification of wireline logging. Wireline logging tools are broadly classified into 3 sections. Lithology logs, such as spontaneous potentia and gamma ray. Porosity logs, example, sonic/acoustic, neutron, and formation density. Saturation, resistivity, logs, examples are normal and lateral devices, ladder logs, induction logs. Lithology logs. The lithology of a rock unit is a description of its physical characteristics visible at outcrop, in hand or core samples, or with low magnification microscopy. Physical characteristics include color, texture, grain size, and composition. The presence of 2 or more minerals significantly increases the difficulty of determining lithology from wireline logs. All the logging response equations can then be set up for each measurement, such as the density, neutron, and sonic. The unknowns must be less than or equal to the number of equations for a unique solution to be obtained. A paramount fact that must be kept in mind is that the number of variables that are being computed cannot exceed the number of equations. For example, if the density, neutron, and sonic logs are being used, the total number of equations that can be set up is 4, 1 for each of the measured logs and the 4th for the material balance equation. In short, lithology logs are designed to identify permeable formations, determine boundaries between permeable and non-permeable formations, provide lithology data for correlation with other wells, provide a degree of certainty for quantifying the formation lithology. Examples are spontaneous potentia, and gamma ray. Porosity logs. Porosity logs measure the fraction or percentage of pore volume in a volume of rock. Most porosity logs use either acoustic or nuclear technology. Acoustic logs measure characteristics of sound waves propagated through the wellbore environment. Nuclear logs utilize nuclear reactions that take place in the downhole logging instrument or in the formation. Nuclear logs include density logs and neutron logs, as well as gamma ray logs which are used for correlation. The basic principle behind the use of nuclear technology is that a neutron source placed near the formation whose porosity is being measured will result in neutrons being scattered by the hydrogen atoms, largely those present in the formation fluid. The difference between neutron porosity and electrical porosity measurements indicates the presence of hydrocarbons in the formation fluid. In short, porosity logs are designed to provide accurate lithologic and porosity determination, provide data to distinguish between oil and gas, provide porosity data for water saturation determination. Examples of porosity logs are sonic or acoustic, neutron, and formation density. Saturation or resistivity logs. Saturation logging allows further insight into the movement of all fluid contacts in the reservoir with time, be it from gas cap expansion seen in some of the thin oil rim reservoirs, or aquifer encroachment as observed from the gas-water and oil-water interfaces. This knowledge of the strength and direction of water movement supports more accurate production forecasting for base well stock by assisting with predicting the time to water breakthrough in reservoirs, reducing one of the more significant subsurface uncertainties. In short, these are designed to determine the thickness of a formation, provide an accurate value for true formation resistivity, provide information for correlation purposes, provide a quick indication of formation pressure, hydrocarbon content and producibility. Examples of saturation logs are normal and lateral devices. Lateral logs. Induction logs. Thank you for learning with us.